In this video, we're going to start talking about intermolecular forces. So if you remember from general chemistry, intermolecular forces are the connections between particles. So if I had solid water, what's the connection that holds one water molecule to a neighboring water molecule? So those are our intermolecular forces. Abbreviated IMF, because intermolecular forces is a lot to write every time. So these were the interactions between molecules. And oftentimes the functional group determines the intermolecular forces. So the type of intermolecular forces that the compound has. Remember, our functional groups were similar structural characteristics that determine the physical and chemical properties of our substance. So, and we will review some of this, but if you do remember your intermolecular forces from the past, alcohols, because I have that oxygen bonded to hydrogen and a lone pair of electrons on that oxygen, is going to have hydrogen bonds. And all alcohols are going to have that. If it's an alcohol, it will have hydrogen bonds because its functional group is this part, and all alcohols are going to have that. It also has dipole-dipole forces and London dispersion forces. If that doesn't sound so familiar to you, we will review it here. So again, the connections between particles in our substance. So now that I erased it, I'm going to draw it back on the board or back on the iPad. But what is the connection that holds, right, one of these to the neighbor? So the red dotted line, these are my intermolecular forces. The bonds within the alcohol itself, those are my covalent bonds. So intermolecular forces, the connections between molecules. So we're going to look at three main types. Our first one are, let's just do hydrogen bonds first, actually, hydrogen bonds. And hydrogen bonds are very specific, so as I write this, it's kind of wordy, just bear with me, and then I'll explain it. So this is the attraction between a lone pair of electrons on an oxygen, nitrogen, or fluorine atom and a neighboring hydrogen that is bonded to an oxygen, nitrogen, or fluorine atom. So the attraction between a lone pair of electrons on an oxygen, nitrogen, or fluorine atom and a neighboring hydrogen that is bonded to an oxygen, nitrogen, or fluorine atom. So two parts to this. You have to have an oxygen, nitrogen, and fluorine with a lone pair on it. And then the other molecule that it's bonded to has to have a hydrogen that's bonded to an oxygen, nitrogen, or fluorine. So you have to have an OH, an NH, or an FH bond, and then you have to have a lone pair on that oxygen, nitrogen, or fluorine. So if we look at that alcohol again, so I got two lone pairs here, and then if I draw my neighboring molecule, so my criteria, I have a lone pair of electrons on an oxygen, and then I have a hydrogen that's bonded to an oxygen on a neighboring molecule. So the connection between that lone pair and that hydrogen is my hydrogen bond. And I guess we'll just leave it highlighted. I want to compare and contrast the next one to this one because it's going to look like I'm drawing my arrows in the same spot and they're actually different. And that might be easier to see when we can compare and contrast them, but it is to that lone pair. So attraction between a lone pair of electrons on that oxygen, nitrogen, or fluorine. So this is my hydrogen bond. Our next one is dipole-dipole interactions. And dipole-dipole interactions exist between polar molecules. It's one of the reasons we needed to review, right, whether a molecule is polar or non-polar, because in order to determine what type of intermolecular forces they have, we need to know that. So this is going to exist between polar molecules. If the molecule is non-polar, it's not going to have dipole-dipole interactions. So it has to be polar. And what it is the partial positive atom of one molecule is attracted to the partial negative atom of a neighboring molecule. So I'm going to use the alcohol again as my example, and I'm going to draw it actually up above. Sorry if this is confusing, but I want to have them in the same view so we can look at them. So this is going to be my example for dipole-dipole, and I'll actually write that on there like I did the hydrogen bond so you can see. So oxygen, and if I was to label my partial charges on here, oxygen's more electronegative, hydrogen and carbon are both partial positive, partial negative, and partial positive. So if I wanted, which I'm going to, I can draw an intermolecular force. I can draw a connection between this oxygen and hydrogen, which looks just like what I did on the other one, but I left the lone pairs off of this one on purpose because this one is actually between the oxygen atom, not the lone pair of electrons on oxygen. So dipole-dipole. So it's this oxygen being attracted to that hydrogen. If I go back, let's take that highlighter off, I'm just going to put it back on, but the hydrogen bond is between the lone pair and the hydrogen. So it's a very small but important difference. You can have dipole-dipole interactions between partial positive and partial negative charges, even if you don't have a lone pair. You have to have a lone pair, right? We have to have a lone pair on our oxygen, nitrogen, or fluorine, and then a hydrogen that's bonded to an oxygen, nitrogen, or fluorine on the one that it's being, attracted to. So be careful. It kind of looks like they're the same. If I ask you to draw one like on a problem set, be very specific as to whether you're drawing it to the lone pair or if you're drawing it to the atom itself. Hopefully that distinction is making some sense for you. Our next one goes by a gazillion names. I call them London dispersion forces. That's probably how you learned it in general chemistry. So I'm going to stick with that name just for consistency. Usually I'll abbreviate LDF because it's another one that's obnoxious to write every time. But it's also, your book calls them van der Waals forces. So this is how you're going to see it in your text. And if you go on and take biochem, you're probably going to see van der Waals forces also. It's an older term, but it's still used a lot. So van der Waals forces and London dispersion forces are the same thing. It also goes by a gazillion other names. You could just do London forces and drop the dispersion. You could actually do dispersion forces and drop the London. Sorry, there's more too. You could also say induced dipole, all of these are the same thing. So London dispersion forces is the term I'm going to use most often. Van der Waals forces is the one your text is going to use. London forces, dispersion forces, same thing. And then induced dipole, that one's becoming more common just because we have dipole, so to kind of like have them sound similar. This one exists between all particles if they have electrons. So this is going to be the only one that our nonpolar molecules have. If it's polar, it can have dipole-dipole interactions also. And if it has an oxygen, nitrogen, or fluorine with a lone pair and a hydrogen bonded to an oxygen, nitrogen, or fluorine, it can also have hydrogen bonds. If it's not polar though, if it's non-polar, this is its only option. So this is the only one that non-polar forces or non-polar bonds experience. And we're just going to say all molecules, and we can actually add atoms and ions experience this force. And then I'm going to give us one exception as long as it has electrons. What's something that wouldn't have electrons? We talked about it a lot in the last chapter. Yeah, hydrogen ions, right? Hydrogen ions don't have any electrons, which is why we can call them a proton, right? No neutrons neither. So essentially everything except for H plus can have these. We can add, it's the only one, the only intermolecular force between non-polar molecules. London dispersion forces are one of the kind of weirder ones to think about. So again, a big wordy explanation, so just kind of bear with me and then I'll try to explain it better. So these result from a weak temporary dipole caused by the unsymmetrical distribution of electrons. And it's an induced dipole. We should put that in there. So results from a weak temporary induced, if you can squeeze that word in your notes, that would be good, caused by the unsymmetrical distribution of electrons. So again, a lot of words that might not make a lot of sense. So we're gonna draw a little picture. So I have an atom, totally not to scale, right? Remember, if that was the size of my nucleus, then my electron that I'm about to draw should like be in the next room, right? This would not fit on my iPad. But we are gonna draw a couple electrons on here. And then I have a neighboring atom, and it has a couple electrons also. And then remember, the electrons are moving, and we're not using Bohr's model, right? We're using quantum mechanics, so they're following a wave-like pattern. And they don't have to travel like together, they're traveling independent of each other. So as those electrons are moving around in that atom, it's very possible, and I'm gonna move these because they're moving, it's totally possible that those electrons get bunched up on one side, right? Because they're moving constantly. So if they're bunched up on one side, and then let's say we can freeze time, what are the electrons on my left atom going to do to this electron on my neighboring atom? What do like charges do? Yeah, good. Like charges repel. So those electrons on my left atom are going to cause that neighboring electron, right, the electron in the neighboring atom, to be moved to the other side. And that's the induced part. So the bunched up electrons, right, the unsymmetrical distribution, so bunched up on one atom, is causing an electron in the neighboring atom to move. And what we have now is a temporary dipole. So if I look at the atom on the left, this side of it is partial negative because the electrons are bunched up on it, right? This side would be partial positive because the electrons are on the other side. Same thing with this. This side is partial positive because the electrons are bunched up on the other side, right? They're unsymmetrically distributed. So between this partial negative side and this partial positive side, I can have an intermolecular force. So it's weak, it's temporary because we can't freeze time, right? We unfreeze time, the electrons move over and we break that intermolecular force, that London dispersion force. So we're constantly making and breaking these. If you have electrons, which most things do, right? Hydrogen ions would not, but if you have electrons, they can be arranged at any given moment unsymmetrically. And then they can cause neighboring electrons to move, setting up this weak temporary dipole. So we're constantly making and breaking these. The more electrons you have, of course, the stronger this effect is going to be. The less electrons, the less you can have. So that's our next statement here, is that London dispersion forces tend to be weak, but the strength varies greatly. Right? Each one individually is pretty weak, but if you have a really big molecule with lots of electrons, then they sum to be substantial. Right? Large molecules with many electrons. The London dispersion forces sum to be substantial. So kind of the two trends, we could say larger atoms or molecules with more electrons have stronger London dispersion forces, right? You just have more electrons moving around. Your odds of them being bunched up on one side are greater. So larger atoms with more electrons have stronger London dispersion forces. And a good example for this, if we were to compare fluorine versus bromine versus iodide. So these are all nonpolar, right? It's just an FF bond, so nonpolar because the atoms have the same electronegativity, so those electrons are being shared equally. Same with bromine, same with iodide. And if you remember back to your 130 or high school days, fluorine is a gas at room temperature, bromine is a liquid, and iodide is a solid. And remember, what determines whether something's a gas, a liquid, a solid are those connections between particles, right? This is also kind of a little review. If I have a solid, so this is my solid, these dots are my little particles, so in this case it could be iodide, or whatever solid we want to talk about, but all those neighboring particles have lots of connections. Remember those connections, depending on the type of solid, but in this case iodide, they're going to be intermolecular forces. So lots of connections. When we go from a solid to a liquid, we break some of those connections, right? Which is why a liquid has, I didn't want to break all of them. That's why a liquid has a definite volume, but its shape can change, right? It's kind of floppy. We're breaking some of those connections. And then when we go to a gas, we've broken all of those connections. Remember, gas is, I have no connections between particles. Each particle is completely independent of each other, of the other. So how that relates to what we're talking about here is that if those connections are strong, they're harder to break. If those connections are weak, they're easier to break. So at a given temperature, if one thing is a gas and the other thing is a solid, the one that's a gas had weaker connections because at 25 degrees Celsius, which is considered room temperature, we've already supplied enough energy to break those connections. So what we're saying is that the London dispersion forces, because that's all these have, right? They're nonpolar. The London dispersion forces in fluorine are much weaker than those in bromine because they have not all been broken, and they're much, much weaker than those in iodine because I haven't broken any of them at 25 degrees Celsius. And the only difference between these guys is the size, right? They're in the same group, they're both halogens, and as we go down a group in our periodic table, larger and larger shells are occupied with electrons. So in fluorine, my outermost electrons are in my second shell. In bromine, they're out, I'm looking at my periodic table here. In bromine, they're out in my fourth shell, and then in iodide, they're out in my fifth shell. If you look at the total number of electrons, I have 18 for fluorine, I have 70 for bromine, and I have 106 for iodide. So more electrons, stronger London dispersion forces need more energy to break those connections. Right? The only difference between these guys is is what atom it is. The connections between them all are London dispersion forces. It's just that they're stronger in iodide, right? It's a larger molecule. Oop, one of my highlighter. It's a larger molecule with more electrons. So the strength of my London dispersion forces is greater. So that is why, right? Iodine is solid and fluorine is a gas at room temperature. It has to do with those connections. Our other trend is if we have molecules that have the same number of electrons but different shapes. So molecules that have the same number of electrons but different shapes. So these would be isomers. The ones with more surface area have stronger London dispersion forces. So more surface area, we could say they're more spread out. And an example for this one, we could do C5H12, this being a saturated molecule, right? Using the formula we learned in our last video, if I have 5 carbons, 2 times 5 is 10 plus 2 is 12, so this would be saturated, this would be an alkane, right? Just carbon and hydrogen. And I could draw different isomers for this. So I could draw all of those in a row, right? 5 carbons in a row. I could do 4 carbons and then stick a carbon on the second carbon. Whether I stick it on that carbon or this carbon, it's the same thing. Those are not isomers of each other. Or I could do 3 carbons and then I could put 2 on each. And then remember, all of these are tetrahedral. So by putting 2 on here, like one is coming out at us and one's going back. And as I go in this direction, these are going to have stronger London dispersion forces. They all are C5H12, so I have the same number of electrons. The only difference is the shape. So the straight chain one is more spread out. This is almost kind of like a little ball. If you were to build a model of it and put all the hydrogens on it, it's almost kind of sphere-like once you put it on there. So even though they're all C5H12, they actually have different boiling points. If you were to look at values for these, they're going to be different. And again, it's just really based on the shape. Why ones with more surface area have larger, stronger London dispersion forces? If we go back up to our picture here, I don't know if this will help a ton, but these 2 atoms have to be in contact with each other, right? If I go and put this electron back, right? They have to come relatively close to each other. They don't have to touch, but they have to get relatively close to each other for this electron to repel that electron. And the more surface area you have, you're just increasing the odds. So more surface area, more contact points, more likely to induce a temporary dipole. So more surface area, more places for the two molecules to come in contact, more inducing of dipoles. So molecules that have the same number of electrons, but different shapes. Forgot a word. Different shapes. The ones with more surface area have stronger London dispersion forces. So let's go through an example. I'm going to give us a few molecules and we're going to rank them in order of increasing strength of intermolecular forces. So the first thing we're going to do is go through and figure out what type of intermolecular forces each have and then rank them. So rank the following. In order of increasing strength of intermolecular forces. So when I say increasing strength, that means number one is going to be the weakest, right? As we go, we want them to become stronger. So number one will be the weakest. And our molecules, as I draw these, think about what functional groups I'm drawing. That would be good practice. I'm going to just move this over. I want to draw two more here and I'm going to run out of room. So let's do functional groups first. Were you guys thinking about that? So this first one, what's my functional group? You have a halogen bonded to a carbon, so that's an alkyl halide. The next two are just alkanes, right? Just carbon and hydrogen, and all of my carbons have single bonds. I have an amine, right? My nitrogen bonded to a carbon. And then this has two alcohol groups on it. Alcohol, remember I have a hydroxyl group bonded to that carbon. So we're going to list our types of intermolecular forces. So in my alkyl halide, and this is one of our defining characteristics of our alkyl halide, is I do have a polar bond, right? Bromine is more electronegative than that carbon, so I do have a polar bond. Those electrons are being pulled towards bromine. So because it's polar, this is going to have dipole-dipole interactions, or dipole-dipole forces, same thing. You could even say dipole-dipole bonds if you really wanted to. And then it's also going to have London dispersion forces, right? It has electrons, it's going to have London dispersion forces. And honestly, I'm not going to give you H+, I'm not going to do that. So everything I give you is going to have London dispersion forces. So if you get a question like this and you have no idea, always write down London dispersion forces and you're going to get partial credit. Literally just write down London dispersion forces for everything and you're going to get some points because they're all going to have them. Alkanes just have carbon and carbon bonds and carbon and hydrogen bonds. And if we remember back to our section on polarity, we said that carbon-hydrogen bonds are considered nonpolar. So our alkanes are always going to be nonpolar. Because it's nonpolar, I'm going to put that in a different color, and then we'll go back and add it to the other one. Because it's nonpolar, it's only going to have London dispersion forces. So nonpolar. Going back to my alkyl halide, just so we can be consistent, that's polar. And then when you go back and look in your notes, you can see why. This next one is also an alkane, so also nonpolar. So it's only going to have London dispersion forces. My amine, what type of intermolecular forces do I have on this one? So I hope you guys are recognizing that it's polar, right? Partial positive, partial negative. So this is a polar molecule. If I was to draw out those hydrogens, nitrogen-hydrogen bonds are also polar bonds. Oop, I was just about to draw my arrow backwards. No, I was going to draw it right, sorry. Right, and then the same with this other one. Didn't quite fit in there. It should be all the way. You guys get how to draw my dipole bonds. But definitely a polar molecule. So if it's polar, it's going to have dipole-dipole forces. I'm always going to write down London dispersion forces, right? It has electrons, they're moving, they can be arranged unsymmetrically, causing neighboring electrons to be distorted. And then what am I missing? I know my picture's gotten kind of messy. I'm going to get rid of actually these dipole arrows, just because I have to add one more thing. What's missing? I don't have any charge. I have partial charge, but there's no formal charge. So there is a lone pair on that nitrogen. Remember, I'm not always going to draw lone pairs, but we know they're there based on the formal charge, and this doesn't have any formal charge. So we know there's a lone pair on there. So this one's also going to have hydrogen bonds. Remember, hydrogen bonds are on molecules where I have a lone pair on oxygen, nitrogen, or fluorine. So I have a lone pair on nitrogen, and then you also have to have a nitrogen-hydrogen bond. So this is a primary amine. Secondary amines also have a hydrogen on them, so they would also have hydrogen bonds. However, tertiary amines do not have a hydrogen on them. If I was to draw a tertiary one real quick, we'll make it look this very similar, but let's put carbon groups on here instead. I have a lone pair on nitrogen, but I don't have a hydrogen bonded to nitrogen. So a tertiary amine is not going to form hydrogen bonds. So do be careful for that. We have to have both criteria, right? A lone pair on nitrogen and then a hydrogen bonded to it. So this one, because it's not a tertiary amine, it does have hydrogen bonds. My alcohols are usually pretty quick for people because they look very similar to water, right? Water would be a hydrogen bonded to an OH group. This is a carbon bonded to an OH group. It's bent in both cases around that oxygen. I have two lone pairs on those oxygens. It's a very similar sort of molecule, just bigger. So my alcohol is definitely going to be polar, right? Let's draw those hydrogens out. Just so we can put our partial charges on them. So oxygen is more electronegative than both hydrogen and carbon. I'm going to leave the dipole arrows off just because it's going to be messy. But again, oxygen is more electronegative than both carbon and hydrogen. That's a plus. So definitely polar. Anytime it's polar, you're always going to write down dipole-dipole because all of our polar molecules are going to have it. We're always going to write down London dispersion forces because it has electrons. And then this one also has hydrogen bonds, right? I have a lone pair on oxygen, and I have two of them. Oxygen is also bonded to hydrogen. So this one can actually form two hydrogen bonds per molecule. Okay, our ranking. So of these, which one is going to have the weakest intermolecular forces? So London dispersion force, and we're just looking to see what they have. Like the two alkanes only have London dispersion forces. So they're going to be weaker intermolecular forces than something that has a dipole-dipole and a London dispersion force. Of those two, though, we can pick because they have different shapes. They're both C4, H10, if you were to add up the number of electrons on there. So this is the one where the more spread out shape, right, more surface area is going to have stronger intermolecular forces. So the one that's more compact is going to have the weaker force. So remember, number 1 is my weakest. So which one's going to come next? Hopefully you guys said this one. It just has dipole-dipole and London dispersion force compared to the last two, which also have hydrogen bonds. And then I'm just going to get rid of, it's really messy and it's getting hard to see. It's not that it's messy, it's just busy. So between these two, the alcohol, I have 2 hydroxyl groups on there, so I can form 2 hydrogen bonds per molecule. On my amine, I only have one of those amine groups, so it can only form 1 hydrogen bond per molecule. So the one that can form 2 is going to have stronger connections. So this is going to be number 4, and this is going to be 5, my strongest.